Every detail in this story comes from real scientific research and observation. Imagine a light so bright it outshines an entire galaxy. Not a galaxy with 100 stars, not 1,000, a galaxy with 200 billion suns, and a single event in a single second burning brighter than all of them combined. It was detected by a satellite designed to find nuclear weapons. The year was 1967. The Cold War was at its peak, and somewhere in the instruments of a military spacecraft called Vela, a signal arrived that no one had been looking for. It was not a bomb. It was not a Soviet test. It was something from so far away that the scientists who found it had no category for it yet. They would not tell the public for 6 years. The universe had just introduced itself. In the decades that followed, astronomers would learn that these events, gamma-ray bursts, are the most energetic explosions in the known universe, not the most energetic in our solar system, not in our galaxy, in the entire observable universe, across 13.8 billion years of cosmic history. A single gamma-ray burst, lasting anywhere from a fraction of a second to several minutes, releases more energy than the sun will produce in its entire 10 billion year lifetime. Some of them release that energy in 2 seconds. 2 seconds. You will breathe in and out before it is finished, and in that time, something 4 billion light years away will have burned brighter than any other object in the sky. There is a burst on record that occurred when the universe was 400 million years old. The light from that burst arrived at Earth in 2009. It had been traveling for 13.1 billion years. You were alive in 2009. There is a jet of material inside these explosions, a narrow beam of plasma and radiation, moving at 99.9994% of the speed of light. At that velocity, the relativistic effects are not minor corrections. They change what time means. They change what distance means. The jet does not experience the universe the way you do. There are scientists who believe a gamma-ray burst within a few thousand light years of Earth would strip the ozone layer, not damage it, strip it, expose the surface to ultraviolet radiation, intense enough to trigger mass extinction. Some researchers believe this already happened once, 440 million years ago, the Ordovician extinction, half the species on Earth gone, and no one knows for certain what caused it. Tonight, you will hear about the 2 neutron stars that spiraled toward each other for billions of years. Their orbit decayed, light second by light second, millennium by millennium, until they were close enough to touch. When they merged, in a fraction of a second, they released more energy than the sun has produced in its entire lifetime, and the gravitational wave from that collision arrived at a detector in Louisiana at the same moment as the gamma-ray flash. 2 completely different messengers, 2 completely different kinds of waves, both carrying the same story. The universe sent the same message twice, in 2 different languages, at the exact same time. You are going to hear what happened when the scientist realized that. Tonight, you are going to stand at the edge of that light. You are going to travel back to the moment of the very first detection, a room full of confused scientists staring at readouts that should not exist. You are going to follow the light itself, from the dying star that made it, across billions of years of empty space, to the moment it touched a detector orbiting the Earth. You are going to feel what it means to live in a universe where this is happening right now, tonight, while you sleep, in directions you will never be able to point to, from places so far away The light began its journey before the Earth existed. This is Quiet Science at Bedtime. If this is your kind of story, a subscribe means everything right now. Just relax and feel free to let this play as you drift off to sleep. Now, let us begin. For most of human history, the sky above you was a ceiling of fixed points. Stars moved in predictable arcs. Planets wandered slowly against the backdrop of constellations. The universe, as far as anyone could tell, was a quiet place, ancient, stable, and largely indifferent to the small planet it surrounded. That understanding was not wrong, it was simply incomplete. The universe is quiet at the scales we can see with the naked eye. The brightest things in your sky, the moon, Venus, Sirius, are close enough and familiar enough that their light feels steady and safe. They rise and set on schedules. They do not surprise you. The sky you grew up under felt reliable in that way. But instruments extended human vision into frequencies the eye cannot detect, into X-rays and radio waves, into gamma radiation, the highest energy form of light in the electromagnetic spectrum. Gamma radiation is not visible light slowed down or dimmed. It is a fundamentally more energetic phenomenon. A single gamma ray photon carries roughly 10 million to 10 billion times the energy of a photon of visible light. When astronomers began placing gamma ray detectors in orbit in the 1960s, the universe revealed a different face. Not quiet at all. Gamma ray bursts are real. They are happening continuously in galaxies scattered across the observable universe. Astronomers detect on average 1 per day. Each one is unique. Each one is unrepeatable. And the science of what they are, and where they come from, and how they are produced, that science accumulated slowly over decades through the work of thousands of researchers building on each other's observations. Tonight, you are going to follow that accumulation from the very beginning. It is the spring of 1967. You are not on Earth. You are in orbit, approximately 118,000 kilometers above the surface, aboard one of a pair of American satellites called Vela. The Vela program was built for a specific practical purpose: to monitor compliance with the 1963 Partial Nuclear Test Ban Treaty, which prohibited nuclear weapons testing in the atmosphere, in space, and underwater. The satellites were outfitted with instruments designed to detect the characteristic gamma ray and X-ray signatures of nuclear detonations. They were orbital watchdogs for the Cold War. For several years, they had done exactly what they were designed to do. They watched, they waited. The readouts were quiet. The gamma ray detectors aboard Vela are solid-state scintillators, crystals that flash with a tiny pulse of visible light when struck by a high-energy photon. The pulses are counted and recorded. Under normal conditions, the count rates are low and steady, reflecting the ambient background of cosmic radiation that fills space at all times. The background is not nothing. Space is not truly empty of radiation, but it is consistent, predictable, the kind of noise that engineers learn to subtract from their data. On July 2nd, 1967, at 1419 Universal Time, the noise stopped being consistent. Both Vela 3 and Vela 4, the pair of satellites flying in formation roughly 200,000 kilometers apart, simultaneously registered an intense burst of gamma radiation. The two detectors spiked together, confirming that the signal was real and not a local instrument glitch. The burst lasted approximately 2 minutes. Within that 2 minutes, the detectors recorded a complex, multi-peaked pulse, not the sharp, symmetrical signature of a nuclear weapon, but something more irregular, more textured, with structure that no weapons designer had ever produced. You sit with those instruments for a moment. The spike has come and gone. The detectors are back to baseline. The event lasted less than 2 minutes, and the readout is now as quiet as it always was. But the numbers are in the record. Something arrived from some direction in space, carrying enough energy to overwhelm instruments calibrated for nuclear tests. And then it stopped. The scientists at Los Alamos National Laboratory, who reviewed the data, did not announce it. They examined it carefully. They ran the numbers against every known source of electromagnetic interference. They checked for satellite attitude anomalies that might have swept a solar particle beam across the detectors. They verified instrument calibration. They consulted with physicists who specialized in nuclear weapons effects signatures, who confirmed what the data already suggested. This was not a bomb, not a Soviet test, not anything human-made. And then they placed the findings in a classified file and continued watching. They were sitting on the discovery of the century, and they did not know it. The frustrating elegance of this moment has a kind of irony that only history can produce. A military satellite, designed to watch for human violence, accidentally pointed itself at something incomparably more violent, happening billions of light years away, and the result was a classified file rather than a celebrated paper. Science sometimes hides its best accidents behind security clearances. More Vela satellites followed. Vela 5A and 5B were launched in May 1969. Vela 6A and 6B followed in April 1970. Each new pair was more sensitive than the last. By 1972, the classified file contained records of 16 separate events, each one different in duration, intensity, and spectral shape, none of them matching any known astrophysical phenomenon, none of them matching any weapons test. Ray Klebosadel, a physicist at Los Alamos, spent months comparing the arrival times of the signals at different Vela satellites. The satellites were separated by hundreds of thousands of kilometers, and a signal arriving from any given direction in the sky would reach each satellite at a slightly different time, the difference depending on the geometry between the satellites and the source direction. By comparing these tiny timing differences, measured to within fractions of a second, Klebosadel could triangulate a rough direction of origin. All of the triangulations pointed in the same general direction, away from the Earth, away from the Sun, away from the solar system. Whatever was making these signals was outside. In June 1973, the paper was published. Observations of gamma-ray bursts of cosmic origin by Klebosadel, Strong, and Olson appeared in the Astrophysical Journal Letters. The title said everything. These bursts were cosmic. They were coming from outside the solar system. Where exactly remained completely unknown. What was causing them remained completely unknown. The field of gamma-ray burst astrophysics was born burdened by a fundamental mystery that would take more than 2 more decades to resolve. Let yourself settle into the particular quality of that era. The 1970s and 1980s were in some ways the most creatively chaotic period of GRB science, because nobody had enough observational data to rule anything out. Proposed mechanisms included flares from neutron stars in the Milky Way's halo, collisions between dense stellar remnants in the galactic center, antimatter annihilation events, evaporating primordial black holes predicted by Stephen Hawking's theoretical work, and even in the more speculative corners of the literature, signals of extraterrestrial origin. That last hypothesis never gained serious traction, but its presence in the literature reflects how genuinely mysterious these events were. When the data is sparse and the phenomenon is extreme, the space of possible explanations is correspondingly wide. The instrument that would begin to narrow that space was BAT-C, the Burst and Transient Source Experiment, one of 4 instruments aboard NASA's Compton Gamma Ray Observatory, launched from the Space Shuttle Atlantis on April 5, 1991. The Compton Observatory was enormous by the standards of space astronomy. It weighed 17,000 kilograms, making it one of the heaviest scientific payloads ever placed in orbit at that time. BAT-C was designed to monitor the entire sky simultaneously for gamma-ray bursts. Its 8 detector modules, positioned at the corners of the spacecraft, gave it an unobstructed view in every direction. When a burst occurred anywhere in the sky, at least one and usually several of the detectors would register it. The relative signal strengths between detectors provided a rough sky position. The temporal profile of the burst, how the intensity rose and fell over time, was recorded with millisecond resolution. You are now aboard the Compton Observatory, looking out through BAT-C 8 eyes. The satellite orbits at an altitude of approximately 450 kilometers, completing one orbit every 96 minutes. Below you, the Earth turns slowly, cloud systems spiraling across blue ocean, the wrinkled brown of mountain ranges, the white caps at the poles. Above you, the sky is black and threaded with gamma-ray sources, the Crab Nebula pulsar, active galactic nuclei, the diffuse glow of cosmic ray interactions throughout the interstellar medium. And then a burst. The detectors spike simultaneously, raw counts jumping by orders of magnitude in the space of a few seconds. The onboard electronics recognize the signature, tag the event with precise universal time, record the full time resolved spectrum, and begin transmitting the data to ground stations. Within hours, the burst parameters are in the hands of astronomers around the world. BAT-C would go on to detect 2,704 gamma-ray bursts during its 9 years of operation, from 1991 to 2000, and from that catalog emerged not just one, but several foundational facts about gamma-ray bursts, facts that would eventually prove essential to understanding what was producing them. The first and most important was isotropy, but the second was almost equally revealing. Gamma-ray bursts divide naturally into 2 distinct populations, separated by duration. Plot the duration of all 2,704 BAT-C detected bursts on a histogram, and something unexpected happens. The distribution is not smooth and bell-shaped. It is bimodal, 2 peaks, separated by a gap, centered around approximately 0.3 seconds on the short side and approximately 20 seconds on the long side. The dividing line falls at approximately 2 seconds. Bursts shorter than 2 seconds belong to one population. Bursts longer than 2 seconds belong to another. Short gamma-ray bursts and long gamma-ray bursts. The distinction in duration is real, but it is not just about time. The 2 populations also differ in their spectral hardness. The ratio of high energy to low energy photons in the burst's gamma-ray emission. Short bursts tend to be harder, with more energy concentrated at higher photon energies. Long bursts tend to be spectrally softer. 2 populations, 2 spectral characters, 2 duration distributions. This bimodality was a clue, though it would take years to decipher fully. What it was pointing toward was the possibility that short and long gamma-ray bursts are not the same kind of event at all, that they are produced by different physical processes in different environments involving different progenitor systems. The eventual answer: they are. Long bursts come from the death of massive stars. Short bursts come from the collision of compact objects, neutron stars with each other, or with black holes. Two completely separate cosmic catastrophes, both capable of producing the same brilliant flash of gamma radiation, both occurring in different types of galaxies at different stages of cosmic evolution. But in 1991, none of this was yet known. What was known was that 2,704 bursts had been detected, that they were isotropic, that they came in two flavors, and that their energetics, if they were cosmological, defied explanation by any known physical process. Isotropic means distributed equally in all directions. BATC's catalog showed no concentration toward the plane of the Milky Way, where the vast majority of our galaxy's stars reside, no concentration toward the galactic center, no preference for any direction in the sky whatsoever. Plotted on a map of the sky, they look like a fine spray of paint thrown randomly at a sphere. If they were local, they would cluster. They did not cluster. Consider what this means through a simple thought experiment. If you stand inside a city and listen to traffic sounds, those sounds come predominantly from the roads around you, concentrated in certain directions, absent in others. But if you rise far above the city, high enough that the entire city is a small patch below you, the sounds blur into an even hum from all directions. The distribution tells you where you are relative to the source. The isotropic distribution of gamma-ray bursts told astronomers where they were relative to the sources, not in the middle of them, not surrounded by a local population of gamma-ray burst progenitors, far outside any coherent structure that could impose a preferred direction. The bursts were cosmological, coming from the deep universe, distributed like a fine powder thrown across the entire observable sky. And if they were cosmological, if they were billions of light years away, then the energy required to produce them was not merely exotic. It was, by the standards of classical astrophysics, almost unthinkable. An event releasing, in seconds, the energy equivalent of converting the entire mass of the sun directly into gamma radiation with perfect efficiency. No known process could do this. The debate over distances reached its formal peak at a symposium held at the Smithsonian Institution in Washington in April 1995. Two astronomers, Donald Lamb of the University of Chicago and Bohdan Paczynski of Princeton University, presented opposing positions in a structured debate modeled explicitly on the 1920 Shapley-Curtis debate over the nature of nebulae. Lamb argued for a galactic distribution. Paczynski argued for a cosmological one. The audience voted. The vote was essentially split. History, as it turned out, was not. Less than 2 years later, the Italian-Dutch satellite Bepo-Sax changed everything. Bepo-Sax carried both a wide-field gamma-ray monitor and, crucially, a set of narrow-field X-ray telescopes that could be repositioned to follow up gamma-ray triggers within hours. The key innovation was not the gamma-ray detection itself, it was the X-ray follow-up. Because gamma-ray bursts, it turned out, produce not just a prompt gamma-ray flash, but a slower fading afterglow, emission that continues for hours to days across a range of wavelengths, from X-rays down through visible light and into radio waves as the blast wave from the explosion sweeps through and shocks the surrounding material. On February 28, 1997, BeppoSAX detected a burst now designated GRB 970228. The gamma-ray signal lasted approximately 80 seconds. Within 8 hours, a timescale previously impossible in this field, the narrow-field X-ray telescopes had slewed to the position and found a fading X-ray source. The coordinates were precise enough to point optical telescopes. Ground-based observatories on La Palma in the Canary Islands turned to those coordinates within 21 hours of the burst. They found a fading point of light, and around that fading point of light, barely visible, was a smudge, extended, diffuse, the unmistakable signature of a distant galaxy. Subsequent spectroscopic observations confirmed a redshift of approximately 0.695. Distance approximately 8 billion light-years. The debate was over. In. Out. Take a slow breath and let the numbers settle. 8 billion light-years. 8 billion years of travel. Light that left its source before the Earth existed, crossing the entire span of cosmic history, arriving at a detector the size of a dining table in low Earth orbit on a cold February morning. The story of that light, where it came from, what made it, how it crossed the universe, that is where we go now. But first, let yourself feel the particular quality of what just happened in this room. Science, at its core, is a slow process of elimination, decades of uncertainty, arguments in print and at symposia, data accumulating piece by piece, and then a single observation, a narrow-field X-ray telescope slewing to a position, a fading point of light, a spectral line at the wrong wavelength, and the argument is over. This is how the universe is understood. Not through revelation, through patience. The patience of astronomers is measured in decades. The patience of the universe is measured in billions of years. Consider what patience actually means in this context. The scientists who built BeppoSAX began planning the mission in the early 1980s. By the time GRB 970228 was detected and localized, and its host galaxy identified, those scientists had spent more than 15 years working toward the capability that made it possible. And before them were the scientists who built the Vela satellites and detected the first burst in 1967. And before them were the physicists who developed the theory of gamma radiation. And before them were the mathematicians who worked out the equations of electromagnetism that describe light at all wavelengths. The chain of knowledge that produced the redshift measurement of GRB 970228 runs back centuries. Every measurement stands on top of an invisible tower of prior measurements, prior theories, prior failures, prior revisions. This is what makes confirmed distances meaningful. They are not readings off a ruler. They are the endpoint of an enormous collaborative effort by thousands of people across multiple generations, all converging on a number that, once confirmed, is as reliable as anything human science has ever produced. 8 billion light-years. That number is reliable. Something is happening right now in a galaxy you will never see that will not reach a human detector for another billion years. That thought carries you gently forward, into the distance, into what the light crossed to get here. The universe does not announce its distances. When you look at a star, you see light. That light tells you the star exists. It tells you something about its temperature and composition. but the light itself arriving at your eye carries no label that reads, "This object is 400 light years away," or 4,000, or 4 billion. Distance in astronomy is not observed, it is inferred. And inferring it requires a chain of reasoning so careful, so layered, so dependent on multiple independent lines of evidence agreeing with each other that each new confirmed distance is a small scientific achievement in itself. The distance to the moon was measured by bouncing radar pulses off its surface. The distance to nearby stars was measured by parallax, the tiny shift in apparent position as Earth moves around the sun, the same geometric principle behind the way your thumb appears to shift against a distant wall when you alternate closing each eye. The distance to galaxies beyond the reach of parallax was measured by standard candles, objects whose intrinsic brightness is known, so that their apparent brightness can be converted to distance through the inverse square law. For gamma-ray bursts, the tool is redshift. You are going to understand redshift now because it is not just a technique, it is a window. What redshift reveals about a gamma-ray burst is not just a number, it is a relationship between the burst and the age and expansion history of the universe itself. Start with something you already understand, the Doppler effect. When a source of sound is moving toward you, the sound waves it emits are compressed. Each successive wave crest is emitted slightly closer to you than the previous one, so the crests arrive more frequently, producing a higher pitch. When the source moves away, the waves stretch, crests arrive less frequently, and the pitch drops. You have heard this your entire life. An ambulance approaching sounds different from an ambulance departing. Light behaves identically. Light is a wave, and if a light source is moving away from you, the wavelength of its light increases, shifted toward the red end of the spectrum, where wavelengths are longer. If the source approaches, the wavelength decreases, shifted toward blue. The universe is expanding. This is not a statement about galaxies moving through space the way an ambulance moves through air. It is a statement about space itself. The fabric of space, the geometry of the cosmos, is stretching, and as it stretches, everything embedded in it moves apart. Distant galaxies recede, not because they are flying away, but because the space between them and us is growing. Light traveling through this expanding space is carried along with it. A photon emitted by a distant galaxy and traveling toward Earth for billions of years arrives at a longer wavelength than it was emitted with because space has stretched during its journey. The wavelength is stretched in direct proportion to how much the universe has expanded since the light was emitted. The ratio of the observed wavelength to the emitted wavelength, -1, is the redshift denoted by the letter Z. A redshift of Z equals 1 means the universe has doubled in size since the light was emitted. A redshift of Z equals 9.4, the measured photometric redshift of GRB 090429b, means the universe was roughly 1/11th its current size when that light left its source. These numbers correspond to real physical distances and real cosmological times. The mathematical relationship between redshift and distance is described by what cosmologists call the Friedmann equations, a set of equations derived from Einstein's general theory of relativity that describe the dynamics of an expanding universe filled with matter and energy. These equations, combined with precise measurements of the current expansion rate of the universe, the Hubble constant, currently measured at approximately 67 to 73 kilometers per second per megaparsec depending on the measurement method, allow astronomers to convert any redshift into a co-moving distance and a look-back time with high confidence. For GRB 090429b, a redshift of 9.4 corresponds to a co-moving distance of approximately 13.1 billion light-years and a look-back time of approximately 13.1 billion years. These are not estimates in the loose sense. They are values derived from a well-tested theoretical framework, cross-checked against independent measurements from Type 1a supernovae, the cosmic microwave background, and baryon acoustic oscillations, three entirely different physical phenomena that all converge on the same cosmological model. The universe has a consistent geometry, and the tools to measure it have been refined over decades. When a redshift is measured for a gamma-ray burst, the distance that follows is as firmly grounded in physical reality as any measurement in science. For gamma-ray bursts, the redshift is measured from the spectrum of the optical afterglow. The burst's fading light, caught by a spectrograph attached to a large ground-based telescope within hours of detection, is spread into its component wavelengths. In that spectrum, astronomers look for the characteristic absorption lines of hydrogen, oxygen, magnesium, silicon, elements present in gas clouds along the line of sight between the burst and Earth. Each element absorbs light at specific rest frame wavelengths, known to high precision from laboratory measurements. If those absorption lines appear shifted to longer wavelengths by a consistent factor, that factor reveals the redshift, and from the redshift, the distance follows. This sounds clinical when described this way. In practice, it is a race. When a gamma-ray burst is detected by a satellite like SWIFT or Fermi, an automated alert goes out within seconds to every major observatory on Earth with a suitable view of the sky. Telescopes slew automatically. Spectrographs are prepared. The optical counterpart, the fading afterglow, is identified within minutes, and then the spectrograph begins collecting light, spreading it into a rainbow of wavelengths, looking for the shifted lines that will reveal the distance. But the afterglow fades. It fades quickly, a burst that is visible to a modest telescope an hour after detection may be invisible to the largest telescopes on Earth 6 hours later. The race against the fading light is real. Missed opportunities are common. Every clear measurement requires coordination across time zones, across telescope schedules, across weather systems that no one controls. The data that has been successfully collected tells a story that builds in scale with each new entry. GRB 970508, detected in May 1997, redshift 0.835, distance approximately 6 billion light-years. This burst became the first GRB with a confirmed spectroscopic redshift, the first direct proof of cosmological distances. Astronomers at the 10-meter Keck telescope in Hawaii measured absorption lines shifted by a factor of 1.835 from their rest frame positions. 6 billion light-years. The field was electrified. GRB 971214, detected in December 1997, redshift 3.42, distance approximately 12 billion light-years. The isotropic equivalent energy, the energy that would be observed if the burst were emitting equally in all directions, was calculated at approximately 3 × 10 to the 53 joules. The Sun emits approximately 3.8 × 10 to the 26 joules per second. GRB 971214 released, in approximately 35 seconds, roughly 10 times the total energy the Sun will emit over its entire 10 billion year main sequence lifetime. In 35 seconds. GRB 080916C, detected by the Fermi Space Telescope in September 2008, redshift 4.35, duration approximately 23 seconds, isotropic equivalent energy of approximately 8.8 times 10 to the 54 joules. The minimum Lorentz factor of the emitting material, the relativistic compression factor, describing how close to the speed of light the jet was moving, was constrained to be greater than 887. At that Lorentz factor, the material streaming outward from the collapsing stellar core was moving at a velocity at least 99.9994% of the speed of light. Try to hold that, not just fast, not approaching the speed of light in the approximate way a bullet might be said to approach the speed of sound, moving at 99.9994% of the speed of light. At that velocity, the relativistic effects described by Einstein's special theory of relativity are not minor corrections. They are the dominant physics. Time is compressed, distances are contracted, energy is multiplied. The jet exists in a different relationship to space and time than anything in ordinary human experience. And then there is GRB 090429b. Detected on April 29, 2009, by the Swift satellite, this burst has a photometric redshift of approximately 9.4, a distance so great it places the source in the universe's first 400 million years. Less than 3% of cosmic history had elapsed when that light began its journey. Let that number arrive without trying to domesticate it. 400 million years after the Big Bang, the first stars had only recently ignited. These were stars unlike any in the present-day universe, composed almost entirely of hydrogen and helium, with essentially no heavier elements, because the heavier elements had not yet been synthesized in stellar interiors and scattered into the interstellar medium. Without carbon, without oxygen, without metals in the astrophysical sense, these first stars formed differently than modern stars. Theoretical models suggest they were far more massive, some perhaps hundreds of times the mass of the Sun. The first galaxies were assembling around these massive, hot, brilliant stars. They were small and irregular, nothing like the grand spirals visible in today's sky. The intergalactic medium was in the process of being reionized by the ultraviolet light from the first stars and early quasars, a transition called the epoch of reionization that fundamentally changed the transparency of the cosmos. GRB 090429b occurred in the middle of this epoch. The burst that produced it, almost certainly the collapse of one of these early massive stars, illuminated for a brief moment the universe as it was when it was young. The light from that moment has been traveling ever since. During that journey, the universe changed around it. The first generation of massive stars died and scattered their synthesized heavy elements into the interstellar medium. Second-generation stars formed from that enriched material, stars that could now form planets because the heavier elements existed. Our own solar system condensed from a cloud of gas and dust approximately 4.6 billion years ago. The light crossed the universe as Earth cooled, as the first oceans formed. As life began, as that life gradually complexified, as the first animals moved through ancient oceans, as continents drifted, as the dinosaurs flourished for 160 million years and then disappeared, as mammals inherited a warming world, as one lineage of primates descended from trees, stood upright, developed language, built cities, turned scientific instruments toward the sky. In 2009, a satellite called SWIFT detected a gamma-ray burst. Its alert system triggered within seconds. Ground-based telescopes slewed to the coordinates. An afterglow was found. Its spectrum was measured. The redshift, extracted from the fading signal, revealed the distance. You were alive in 2009. You may have been going about your day at the exact moment that light, which had been traveling since the universe was 400 million years old, arrived at Earth and was detected. The universe connects moments across scales that ordinary language cannot hold. Now think about what that light itself carries. A gamma-ray burst afterglow is not just a bright spot to measure and record. It is a message, and the message is layered. The absorption lines imprinted on the afterglow spectrum carry information about every cloud of gas the light passed through on its journey. Each cloud leaves a fingerprint, a set of absorption features at specific wavelengths, shifted by the redshift of that cloud. By reading those fingerprints, astronomers can study the composition and distribution of gas across billions of light years of cosmic history. A single gamma-ray burst afterglow, observed carefully, is a map of the universe between here and the source. Astronomers estimate that the observable universe produces, on average, approximately one detectable gamma-ray burst per day at Earth's position, but this is not the actual rate, because GRBs release their energy in a collimated beam rather than uniformly in all directions. Most bursts in the universe are never detected. The jet simply points elsewhere. Accounting for this geometry, the true rate of gamma-ray bursts in the observable universe is estimated to be hundreds of thousands per day. Every day, hundreds of thousands of gamma-ray bursts, each one representing the death of a massive star or the collision of two collapsed stellar remnants, each one releasing in seconds the energy output of hundreds of billions of suns. This is not a rare event. This is routine. The universe has been doing this since the earliest stars formed. It will continue doing it as long as massive stars exist to die, and the light from each event, spreading outward at the speed of light, will travel forever, crossing the expanding fabric of space, carrying information about the source and about everything it passes through, until something intercepts it or the expansion of the universe dilutes it beyond detection. Most of it will never be detected. Most of it will travel forever in the darkness between galaxies, never touching another atom, carrying its information into an infinite and empty future. The fraction that reaches us is a tiny, almost incomprehensible fraction of the total light produced. And yet it is enough. It is enough to reconstruct the distances, to measure the redshifts, to map the intervening gas, to probe the conditions of the early universe, to ask and begin to answer the question of what physical mechanism inside a dying star can release this much energy in this short a time. That question waits ahead. But for now, the distances hold you. Your breath is slow, your body is heavy with the pleasant weight of stillness. The numbers are softening at their edges, losing their arithmetic precision and becoming something else, a sense of immense depth in all directions, a universe that is older and wider and more energetic than any human civilization had ever imagined, and yet legible, at least in part, through patient observation and careful measurement. You are small in it. That is not a frightening thought. It is a restful one. Somewhere right now, At a distance our instruments could measure and our equations could describe, a star is in its final hours. The light from what is about to happen is already forming. You will hear about it next. But for now, the distance is enough. 13 billion light years. The light crossed it and arrived and was measured. And you in the dark have traveled that distance too, not in body, but in the only way human beings ever truly travel anywhere. In understanding, your breath is slow. The numbers no longer have hard edges. They have become something softer, a quality of the dark around you, a sense of the depth behind every direction you could look, up through the ceiling, through the atmosphere, through the solar system, through the Milky Way, through the intergalactic medium, through the early universe, all the way to the moment when a star collapsed and a jet formed and gamma rays began their crossing. And arriving here, and being detected, and being measured, and being understood imperfectly but genuinely by a species that did not exist when the light began its journey. That is what happened. That is real. You are part of a universe that does this, a universe that makes violent, extraordinary events at its largest scales, and also makes patient, curious minds at its smallest scales, and somehow those two things, the violence and the curiosity, combine into the act of science, the act of measuring, the act of understanding. You do not need to hold all of it. You only need to let it rest in the room with you, somewhere in the background of your softening awareness, while your body does what it knows how to do. Rest. Slow down. Release. The universe has time. There is a star at the center of this story. You will never see it. It does not exist anymore. It burned for approximately 3 million years, a lifespan that sounds long until you compare it to the sun's expected 10 billion years, and realize this star lived and died in roughly 3/10,000ths of the time our sun will spend on the main sequence. It was massive, perhaps 40 times the mass of the sun, perhaps 60. Stars at that scale do not age gracefully. They burn their fuel so fast at such extreme core temperatures that they exhaust in millions of years what smaller stars stretch across billions. They live violently and end violently, and the end, when it comes, happens so fast that the word explosion barely captures it. The end takes less than a second. You are going to be there for it. Not at a safe distance, not watching through an instrument. You are going to be close enough to feel the geometry of the collapse, the pressure gradient reversing, the shock wave forming, the jet assembling itself from nothing and accelerating outward faster than anything in ordinary experience moves. Everything you have heard so far, the detection in 1967, the decades of mystery, the redshifts, the distances, all of it was the light arriving at the end of a journey. Now you go to the beginning of that journey, to the star, to the moment its core gives out, to the physics of what happens next. A massive star, the kind capable of producing a long gamma ray burst, spends most of its life in a state of equilibrium that is, when you examine it closely, a constant war. On one side, gravity, the gravitational pull of the star's own mass, directed inward, always pulling every layer of stellar material toward the center. Gravity never rests, it never weakens. For a star of 40 solar masses, the gravitational force pressing inward at the core is immense beyond any terrestrial analogy. On the other side, radiation pressure and thermal pressure. The energy released by nuclear fusion in the core, the conversion of lighter atomic nuclei into heavier ones, releasing the binding energy difference as photons and heat, pushes outward. As long as fusion continues, the outward pressure balances the inward pull of gravity. The star maintains a size, it holds itself up. This balance is called hydrostatic equilibrium. You are standing at the core of this star right now. The temperature here is approximately 3 billion degrees Kelvin. The density is so high that a cubic centimeter of core material would weigh several 100,000 kilograms on Earth's surface. The pressure is measured in units that require scientific notation even to write. In the shells surrounding the core, each layer burns its own fuel, hydrogen to helium at the outer edges, progressively heavier elements in each deeper shell, until the innermost shell is converting silicon into iron. Iron is the end of the line. You can feel it coming, the way you feel a sound that hasn't arrived yet. Iron is the most tightly bound nucleus in nature. To fuse iron into heavier elements requires an input of energy rather than releasing energy. The reaction runs backward energetically. When the stellar core becomes iron, the fusion fire that has held the star up for millions of years simply stops producing the energy needed to maintain pressure. Hydrostatic equilibrium fails. The core collapses. What happens next occurs in approximately 1 second. 1 second of physical processes so extreme that they represent the limit of what matter can do, the absolute frontier of nuclear and particle physics, played out at stellar scale. The iron core, which had a radius of approximately 7,000 kilometers, roughly the size of Earth, collapses to a radius of approximately 10 to 12 kilometers in less than a second. The density increases by a factor of roughly 10 to the 14th. A teaspoon of the resulting material would weigh approximately 1 billion tons on Earth's surface. The collapse is halted, abruptly, violently, by the strong nuclear force. When the density reaches nuclear density, approximately 2.7 times 10 to the 14th grams per cubic centimeter, neutrons packed so tightly they are essentially touching, the nuclear force provides a sudden, extraordinarily stiff resistance. The collapsing material hits this resistance and bounces. The bounce generates a shock wave. The shock wave propagates outward through the infalling stellar material at velocities approaching 15% of the speed of light. As it passes through each layer of the star, it heats the material to temperatures of tens of billions of degrees. It triggers explosive nucleosynthesis, the rapid formation of heavy elements in conditions so extreme they are unachievable in any laboratory on Earth. The shock wave stalls. It loses energy fighting its way through the dense, still infalling outer layers of the star, but it is revived by a pulse of neutrinos, particles that barely interact with ordinary matter, but are produced in such staggering quantities by the collapsing core that even their tiny interaction probability is enough to deposit significant energy into the stalled shock front. Approximately 10 to the 58 neutrinos are released in the core collapse. That number needs a moment. 10 to the 58th power, more neutrinos than there are atoms in several thousand Earths, released in a few seconds, carrying away approximately 99% of the total gravitational energy released by the collapse. The luminosity in neutrinos alone, for a few seconds, exceeds the luminosity of all the stars in the observable universe combined. And yet neutrinos interact so weakly with matter that you could pass them through a light year of solid lead, and most of them would emerge unchanged on the other side. The fact that even 1% of them deposit energy into the shock front is due entirely to the extraordinary density of the infalling material. The revived shock wave expels the outer layers of the star. This is the supernova. But for a long gamma-ray burst, the supernova is not the main event. It is the context. Inside the collapsing system, something else is happening, something that requires specific conditions that are not present in every massive star collapse. The dying star must be rotating, rapidly rotating. As the core collapses, conservation of angular momentum demands that the rotation rate increase, the same principle that makes a spinning ice skater accelerate when she pulls her arms inward. A core that was rotating slowly when it was the size of Earth rotates with enormous speed when it has collapsed the size of a city. If the rotation rate is high enough, and if the mass is sufficient, the core does not settle into a neutron star. It collapses further through the neutron star phase into a black hole, or it may first form a rapidly rotating neutron star, a millisecond magnetar, so dense and so charged with magnetic energy that it becomes a different kind of central engine. Either way, the result is a compact object rotating at hundreds of times per second, surrounded by a thick disk of accreting material, stellar debris that did not fall directly in, but spiraled inward along the rotation axis. This disk is the fuel. The magnetic fields threading the disk and the compact object are the mechanism, and the product, the thing this entire system exists to produce, is the jet. You're above the dying star now, positioned along the rotation axis, looking down into the system from outside. Below you, the stellar collapse is complete. The central engine, a black hole of perhaps 3 to 5 solar masses, or a millisecond magnetar spinning 400 times per second, is surrounded by a disk of hot, dense, magnetized plasma. Material is spiraling inward along the equatorial plane. The temperatures in the disk exceed 1 trillion degrees. The magnetic fields are doing something extraordinary. Threading through the compact object and the disk, anchored to the rotating mass, the fields are being wound and compressed by the differential rotation. Energy is being extracted, not from nuclear reactions, not from chemical processes, but from the rotational energy of the central mass itself and from the gravitational energy of the accreting material. This energy, channeled by the magnetic geometry of the system, is being directed outward along the rotation axis. 2 jets form, one upward, one downward. Each one is a narrow beam, perhaps only a degree or two wide, of plasma and radiation accelerated to relativistic velocities. The Lorentz factor of the jet material begins at a few and rises as the jet propagates to hundreds or even thousands. The jet must first escape the star. This is not guaranteed. The star's outer layers are still present, still dense, still falling inward or being expelled by the shock wave. The jet bores through the stellar envelope, losing some energy to the surrounding material, heating and entraining stellar gas, driving a cocoon of shocked material outward around its boundaries. If the jet is energetic enough, it breaks free. It emerges from the stellar surface and encounters, suddenly, a very different environment. Empty space, the interstellar medium, a few atoms per cubic centimeter rather than the trillion atoms per cubic centimeter of the stellar interior. The jet accelerates. Inside the jet, the gamma rays are produced. The exact mechanism is still an area of active research, but the two leading models are internal shocks and magnetic dissipation. In the internal shock model, the central engine does not produce a steady, continuous outflow. It pulses, emitting successive shells of plasma at slightly different velocities. A faster shell catches up to a slower shell and collides. These collisions happen within the jet at distances of perhaps 10 to the 13 to 10 to the 15 centimeters from the central engine. At the collision site, a pair of shocks forms. Electrons at the shock front are accelerated to ultra-relativistic energies, spiral through the jet's magnetic fields, and emit synchrotron radiation. The same physical process produces radio waves and particle accelerators on Earth. In the jet, the electrons are so energetic and the magnetic field so strong that the emission peaks in the gamma-ray band. In the magnetic dissipation model, the jet is more strongly magnetized, and energy release occurs through magnetic reconnection, field lines of opposite polarity annihilating and converting their stored energy into particle energy and radiation. This model naturally produces a smoother emission profile and may better match some observed bursts. In either case, the result is a burst of gamma radiation propagating outward from the source at the speed of light, collimated into the narrow cone of the jet, carrying the energy signature of everything that happened from the moment the core collapsed to the moment the jet broke free. This is the prompt emission. This is the flash itself. It lasts seconds to minutes depending on how long the central engine remains active. Then the central engine winds down, the accretion slows, the jet weakens, but the blast wave continues expanding outward, sweeping up material from the surrounding environment, driving a forward shock into the interstellar medium and a reverse shock back into the jet material. Electrons accelerated at these shocks produce synchrotron radiation across a broad range of wavelengths: X-rays, ultraviolet, optical light, infrared, radio waves. This is the afterglow. You have now followed the event from core collapse to afterglow, the iron core failing, the collapse to nuclear density, the bounce, the shock wave, the neutrino flood, the supernova, the rotation-driven jet, the drilling through the stellar envelope, the acceleration, the gamma-ray flash, the afterglow. All of this in a system that, by the time the gamma rays reach Earth, is billions of light years away and billions of years in the past. And this was a long burst, the death of a massive star. But there is another kind. You heard about it earlier in this story, the two neutron stars spiraling toward each other. That is the short gamma-ray burst, and its origin story is in some ways even more striking because it does not begin with a single dramatic collapse. It begins with patience. Billions of years of it. Two massive stars form together in a binary system, a gravitationally bound pair orbiting their common center of mass. They live their short lives in parallel. The more massive one dies first, collapsing to a neutron star in the same kind of core collapse you have just witnessed. The binary survives the explosion, barely, in many cases, the kick from the asymmetric supernova nearly unbinding the system. But in some fraction of cases, the binary holds together. Now there is one neutron star and one living massive star orbiting each other. Time passes, millions of years. The second star ages, evolves, expands into a red supergiant, and eventually undergoes its own core collapse. Now there are two neutron stars, two objects each roughly 10 kilometers in radius, each roughly 1.4 times the mass of the Sun, orbiting each other in an increasingly tight orbit. And here is where the patience comes in. The orbit decays. Not because of friction, there is no friction in space. Because of gravitational wave emission, two massive compact objects orbiting each other distort the fabric of space-time, and those distortions propagate outward as gravitational waves, ripples in the geometry of space itself, traveling at the speed of light. Producing these waves costs energy. The orbital energy of the binary decreases very slowly as that energy is radiated away. The orbit shrinks. For a typical neutron star binary, the in-spiral from a wide initial orbit to merger takes hundreds of millions to billions of years. The two stars spiral inward, orbit by orbit, approaching each other at a rate that starts imperceptibly slow and accelerates as the orbit tightens. In the final hours, the orbital period has shrunk from days to minutes. In the final seconds, from minutes to milliseconds. The two stars are now separated by a distance smaller than the diameter of Earth. And then they touch. The merger happens in milliseconds. The two neutron stars collide and merge into a single, rapidly rotating object, either a hypermassive neutron star that collapses to a black hole within seconds, or directly into a black hole. The merger ejects a small fraction of the total mass in an extremely neutron-rich outflow. This outflow is where the gold in your jewelry came from. This is not metaphor. The rapid neutron capture process, the reprocess, requires an environment with an extraordinarily high flux of neutrons. Merging neutron stars are one of the few environments in the universe that can provide it. In the neutron-rich ejecta, heavy elements up to and beyond uranium are synthesized in fractions of a second, as free neutrons are captured by seed nuclei faster than those nuclei can undergo radioactive decay. Gold, platinum, lead, uranium, all synthesized in the outflow of a neutron star merger, dispersed into the interstellar medium over thousands of years, eventually incorporated into the dust clouds that collapse to form new stellar systems, including, billions of years ago, ours. The gold in the world was made in a collision like this one, long before the Earth existed, in a merger that lasted milliseconds and scattered its products across a galaxy. Meanwhile, at the center of the merger, the process of jet formation follows the same principles as the collapsor case, a compact central engine surrounded by an accretion disk of merger debris, magnetic fields channeling energy outward along the rotation axis. But this jet is shorter-lived. The central engine winds down faster, and the result is a short gamma-ray burst, duration less than 2 seconds, spectrally harder than long bursts, produced in a different environment associated with older stellar populations in different types of galaxies. For decades, this model was theoretical. Astronomers inferred the mechanism from indirect evidence, the association of short bursts with old stellar environments, the lack of associated supernovae, the spectral differences. But the model was not proven. On August 17, 2017, it was proven. That morning, the LIGO detector in Hanford, Washington, and its sister detector in Livingston, Louisiana, registered a gravitational wave signal. The signal lasted approximately 100 seconds and showed the characteristic chirp of an inspiral, the frequency rising as two masses spiraled inward and the orbital period decreased. The masses were consistent with two neutron stars of approximately 1.17 and 1.36 solar masses. 1.7 seconds after the gravitational wave signal ended, the the Fermi Gamma Ray Space Telescope detected a short gamma ray burst, GRB 170817A. The same event, detected in gravitational waves and in gamma rays, arriving at Earth within 2 seconds of each other, after traveling approximately 130 million light-years. This was the moment the hook promised you. Two completely different messengers, two completely different kinds of waves, both carrying the same story, arriving at Earth at the same time. The gravitational waves were emitted throughout the in-spiral and merger, ripples in space-time itself, propagating outward at the speed of light. The gamma rays were emitted when the jet, formed in the seconds after the merger, punched through the surrounding material and began producing its prompt emission. The 1.7-second offset between the two signals is consistent with the time needed for the jet to form, propagate, and break free of the surrounding merger ejecta before the gamma rays could escape. In the weeks that followed, optical, infrared, X-ray, and radio telescopes around the world targeted the location. They found the kilonova, the optical transient powered by the radioactive decay of the freshly synthesized heavy elements in the neutron-rich ejecta. The kilonova spectrum showed clear evidence of strontium and broader signatures consistent with a range of heavy ore process elements. The gold was there. The platinum was there. The proof was complete. Short gamma ray bursts come from merging neutron stars. Long gamma ray bursts come from the collapse of massive rotating stars. Two types of cosmic catastrophe, two mechanisms for producing the universe's most energetic flashes of light. And in one extraordinary event in 2017, astronomers witnessed both the gravitational wave signature and the electromagnetic signature of the same neutron star merger, confirming decades of theoretical work in a single observational campaign. Your breath is slow and steady. The mechanics of destruction have a strange peace to them when viewed from a sufficient distance. The collapsing core, the forming jet, the merger of neutron stars, all of it violent beyond any human scale, and yet all of it operating according to laws that can be written down, tested, and confirmed. The universe is not arbitrary. Its violence follows rules. That the same physics that governs the nuclear reactions in your cells, the electromagnetic signals in your nerves, the gravitational pull of the earth beneath you, that the same laws, applied at different scales and under different conditions, produce neutron star mergers and gamma ray jets and kilonovae and reprocess nucleosynthesis. The universe is one thing, operated by one set of rules. Every heavy element in your body, every atom of iron, gold, uranium, was made in a star or a stellar collision before the solar system formed. The event that produced the gold atoms closest to you right now may have happened 5 billion years ago. The light from that event, if it was a gamma ray burst, has long since dissipated into the background radiation of the universe. Nothing remains of it except the atoms it scattered, which became dust, which became the solar nebula, which became the sun and the earth and everything on it. You are the product of ancient explosions you will never see. The jet is propagating outward, the afterglow is fading, the heavy elements are dispersing into the interstellar medium, and somewhere, a new chapter of this story is waiting. The instruments that humans built to catch this light, the engineering of detection, the automated systems that wake astronomers in the middle of the night when something new has arrived from the deep universe. The light leaves the source and enters a universe that, in most directions, is almost entirely empty. Not empty in the way a cleaned room is empty, empty in the way that makes a cleaned room seem impossibly crowded. The average density of the intergalactic medium, the space between galaxies, is approximately 1 atom per cubic meter. In the space between galaxy clusters, it is even less. For a gamma-ray photon traveling from its source to Earth, the vast majority of its journey takes place through a near-perfect vacuum, crossing distances that dwarf anything on the scale of a solar system or even a galaxy. But there are instruments waiting. Human instruments, built with extraordinary care, operating in conditions that require extraordinary engineering, designed specifically to catch these photons at the end of their journey and extract from their properties everything that can be known about where they came from and what made them. The first generation of gamma-ray burst detectors, the Vela satellites, the early international networks of gamma-ray instruments, detected bursts but could not localize them precisely enough to follow up with optical telescopes. The fundamental problem was geometric. A single detector registers a signal but cannot determine its direction. To localize a source, you need timing information from multiple detectors separated by a large distance so that the arrival time differences between detectors can be used to triangulate. The Interplanetary Network, a collection of gamma-ray detectors aboard spacecraft distributed throughout the solar system, was built on this principle. By comparing the arrival time of a gamma-ray burst signal at multiple spacecraft separated by millions of kilometers, the network could triangulate burst positions to an error region of arc minutes in favorable cases, though often arc degrees. These positions were precise enough for subsequent searching, but too imprecise for immediate follow-up with narrow-field optical telescopes. The critical breakthrough came not from better localization alone, but from a different approach, catching the afterglow. If a gamma-ray burst produces an X-ray afterglow that fades over hours, and if that afterglow can be localized quickly enough to narrow the error region to arc seconds, then optical telescopes can be pointed at the precise location before the afterglow fades below detection. This was the design philosophy of Swift. The Neil Gehrels Swift Observatory, named in 2018 for the astronomer who led its development, was launched on November 20th, 2004 from Cape Canaveral. It carries 3 instruments that operate in coordination: the Burst Alert Telescope, or BAT, a wide-field coated aperture telescope that monitors approximately 1/6 of the sky simultaneously for gamma-ray bursts; the X-ray Telescope, or XRT, a focusing X-ray telescope that can be slewed to a burst position to measure the fading X-ray afterglow; and the UV/optical telescope, or UVOT, which provides simultaneous ultraviolet and optical imaging. The coordination between these 3 instruments is the key. When BAT detects a burst, the satellite's automated systems compute a rough position, typically accurate to within a few arc minutes, within seconds. This position is transmitted to the ground via the NASA Tracking and Data Relay satellite system, reaching the Swift ground station at Penn State University within 15 seconds of the burst. Simultaneously, Swift itself slews, physically rotates, using reaction wheels to point the XRT and UVOT at the burst position. The slew takes approximately 50 to 70 seconds. Then the XRT begins observing. You are aboard Swift now. You have just rotated. Below you, Earth fills a quarter of the sky. Ahead, the burst position, a tiny patch of sky about 3 arc minutes across, the best position BAT could compute from the gamma-ray arrival directions. The XRT's mirror system, a set of concentric gold-coated shells shaped to graze incidence focus X-rays, begins collecting photons from that patch of sky. Within the first few hundred seconds of observation, a fading point source appears. The XRT measures its position to within a few arc seconds. This position is automatically computed and transmitted to the ground within 3 to 4 minutes of the original burst detection. At observatories around the world, it is the middle of the night at some of them, afternoon at others, dawn at others. Alert messages arrive. Automated telescope systems receive the coordinates and begin slewing. Human observers who have signed up for the alert network feel their phones vibrate and check the message. Some roll out of bed. Some walk from their offices to their telescope control rooms. Some simply monitor remotely. The race is on. The XRT position, accurate to a few arc seconds, is precise enough to identify an optical counterpart. Within minutes, the first optical images are arriving at observers' computers, thumbnail-sized patches of sky showing, in the best cases, a new point of light that was not present in archival images of the same field. This is the optical afterglow. Its brightness, its position, its color, its rate of fading, all immediately scientifically valuable. If a large telescope with a spectrograph is available and pointing in the right direction, not guaranteed because telescopes are always oversubscribed and weather is always uncertain, a spectrum can be obtained within minutes of the burst. That spectrum, if it contains detectable absorption lines, yields the redshift, the distance, the look-back time, the energy. All of this in the span of time it takes you to have a meal. Swift has been operating continuously since 2004. As of the time the script was written, it has detected more than 1,400 gamma-ray bursts. Its rapid response capability has made it the workhorse of GRB science for 2 decades. The XRT positions it provides have enabled redshift measurements, host galaxy identifications, and afterglow studies that would have been impossible with the instruments available to the previous generation. But Swift is not alone. The Fermi Gamma Ray Space Telescope, launched on June 11, 2008, carries 2 instruments. The Large Area Telescope, or LAT, is a pair conversion telescope sensitive to gamma-ray energies from about 20 MeV to more than 300 GeV, a range that extends far above and below Swift's Bay-at sensitivity range. The Gamma-ray Burst Monitor, or GBM, consists of 12 sodium iodide scintillation detectors and 2 bismuth germanate detectors, arranged to monitor the entire sky, not blocked by Earth. Its all-sky coverage and broad energy range make it complementary to Swift, where Swift provides arc-second positions but covers only 1/6 of the sky. Fermi GBM covers the entire unocculted sky but provides only degree-level positions. There are other instruments in the network. The Integral satellite, operated by the European Space Agency, carries gamma-ray and X-ray instruments with good localization capability and has been in operation since 2002. The Agile satellite, an Italian mission launched in 2007, carries a gamma-ray imager and GRB monitor. Conus Wind, a Russian instrument aboard the NASA Wind spacecraft, has been monitoring gamma-ray bursts since 1994 and continues operating, one of the longest continuously operating GRB detectors in history. The InSight HXMT telescope, a Chinese X-ray observatory, has added gamma-ray burst detection capability to its primary mission. The GCAM mission, launched by China in 2020, was designed specifically to search for electromagnetic counterparts to gravitational wave events. All of these instruments are connected through the Gamma Ray Burst Coordinates Network, the GCN, a system established in 1993 by Scott Barthelemy at NASA Goddard Space Flight Center. The GCN distributes machine-readable burst notices within seconds of detection to a list of subscribing observers that now numbers in the thousands. When SWIFT detects a burst, the first automated GCN notice typically goes out within 15 to 20 seconds. It contains the burst time, a rough sky position from BAT, and preliminary parameters. As SWIFT slews and the XRT begins observing, updated notices follow, each one containing a more precise position. Observers who have set up automated systems receive these notices and immediately act on them. Robotic telescopes that operate without a human at the controls, responding to incoming alert messages through automated scheduling software, can be on target within a minute of the burst. The Boots network of robotic telescopes, the Master Global Robotic Net, the Las Cumbres Observatory Network, with its telescopes distributed around the globe specifically to provide 24-hour sky coverage, regardless of local nighttime. All of these respond automatically to GCN alerts. The result is that for many bursts, the optical afterglow is being imaged before the XRT follow-up observation has even completed its first orbit. The data from these early observations, the brightness, the color, the rate of fading, provide constraints on the burst's environment, the extinction in the host galaxy, and sometimes the redshift through photometric techniques. Consider what detecting GRB 170817A required. LIGO, the Laser Interferometer Gravitational Wave Observatory, measures gravitational waves using laser interferometry. Two perpendicular arms, each 4 kilometers long, have laser beams bouncing between mirrors at their ends. A passing gravitational wave stretches one arm and compresses the other by an amount smaller than 1,000th the diameter of a proton. The detection system is sensitive enough to measure this in the presence of all the seismic, thermal, and quantum noise that fills the world at all scales. Two detectors, Hanford and Livingston, separated by about 3,000 kilometers, observed the same gravitational wave signal with a time delay consistent with a source in the southern sky. The Virgo detector in Italy provided a third measurement. Together, the 3 gravitational wave detectors triangulated the source to a sky region of approximately 28 square degrees. 28 square degrees sounds large. It is approximately 140 times the area of the full moon on the sky, but compared to the earlier LIGO detections, which had error regions of hundreds of square degrees, it was a dramatic improvement. Within 11 hours, optical telescopes searching that region found the kilonova, the optical transient from the neutron star merger in the galaxy NGC 4993, at a distance of approximately 130 million light-years. The search took 11 hours. It found an event 130 million light-years away, confirmed by gravitational waves, gamma rays, X-rays, ultraviolet, optical, infrared, and radio observations, every part of the electromagnetic spectrum, plus space-time itself, carrying the same story. This is multi-messenger astronomy. The term refers to the use of multiple independent channels, different physical carriers of information from the same source, to construct a more complete picture than any single channel could provide. Gravitational waves carry information about the masses and spins of the merging objects and the dynamics of the merger itself. Gamma rays carry information about the jet and its energy. X-rays carry information about the afterglow and the surrounding environment. Optical light carries information about the colonnova and the raw process synthesis. Radio waves carry information about the long-term evolution of the blast wave. Each channel is independent. Each is subject to different physical effects during its propagation. Their agreement, the fact that they all point to the same event in the same location, is a deep confirmation that the physical model is correct. The detection of GRB 170817A required, simultaneously, a gravitational wave network that had been designed, built, commissioned, and improved over decades at a cost of hundreds of millions of dollars. A gamma-ray space telescope that had been proposed, funded, built, launched, and operated for 9 years. Ground-based optical telescopes ranging from small robotic instruments that searched the initial error region to large facilities that characterized the kilonova in detail. X-ray and radio telescopes that followed the afterglow evolution for months, and an international coordination infrastructure that allowed hundreds of researchers across dozens of institutions to share data and analysis in near real time. None of this existed 50 years ago. None of it could have existed 50 years ago. The technologies required, the laser interferometry, the space-based gamma-ray detectors, the rapid communication internet infrastructure that distributes alerts within seconds of detection, were developed incrementally over decades by researchers who often did not know what their work would eventually make possible. You are lying in the dark, and all of that infrastructure is operating right now. The Swift satellite is orbiting Earth at approximately 600 kilometers altitude, circling the planet once every 97 minutes, watching 1/6 of the sky with its Bay-T detector. Fermi is orbiting at approximately 550 kilometers, its GBM watching the entire sky. LIGO Hanford and Livingston are operating, their laser beams bouncing between mirrors and evacuated tubes, sensitive to gravitational wave strains, smaller than anything previously measurable in human history. Dozens of ground-based optical telescopes are open, if weather permits, following up known afterglows or searching for new ones. The universe is being watched. Not completely, not in every direction. There are gaps in the sky coverage, gaps in the energy coverage, gaps in the sensitivity. Many bursts occur in the fraction of the sky not covered at any given moment. Many bursts produce afterglows too faint to detect. Many short bursts fade so quickly that even the fastest robotic telescopes cannot catch them. But the watch is real. And tonight, while you sleep, the instruments are awake. The BAT detector aboard Swift is processing gamma-ray event data at a rate of several hundred events per second, searching for the statistical excess that indicates a burst rather than background. The GBM aboard Fermi is doing the same across its 12 sodium iodide scintillators. The LIGO detectors are running in observing mode, their control systems maintaining the interferometer lock against the constant pressure of seismic noise, thermal fluctuations, and quantum shot noise. If something arrives tonight, a long burst from a collapsing massive star in a galaxy 6 billion light-years away, or a short burst from a neutron star merger at 100 million light-years, the alert will go out within seconds. Telescopes will slew. Observers will be notified. By morning, the data will be in the hands of astronomers who will begin the analysis that will eventually produce a paper, join a catalog, and extend by one more point the growing map of the most energetic events in the observable universe. This is the watch. It is patient, it is continuous, it does not pause for darkness or weather or sleep. In, out. Let the image settle, a network of instruments distributed between orbit and the ground, covering multiple physical channels, coordinated by automated alert systems and human expertise, watching an energetic and violent universe for the next flash of light from the deep past. You are not alone in the dark. The instruments are there. The universe is being observed. There is something quietly reassuring about that. Not because the universe is safe. It is not, and the science of gamma-ray bursts makes clear it has never been. But because the act of watching, the act of building instruments and pointing them at the sky and recording what arrives, is one of the most fundamentally human things a species can do. It is curiosity translated into engineering. It is the desire to understand, made concrete in mirrors and lenses and laser beams and superconducting circuits. It is patience, technical and organizational, sustained across decades by thousands of people who will never individually be famous for it, but who collectively produced the most sensitive astrophysical detection network in human history. The sky is watched. Your breath is slow now. The instruments are awake. Something may arrive tonight, a flash from a dying star in a galaxy whose name no catalog has yet assigned, carrying the record of a collapse that happened before your grandparents were born, before the Industrial Revolution, before the Roman Empire, before agriculture, before human language, before the human species itself. That light is traveling, and the instruments are waiting for it. You do not need to wait with them. You can rest. The watch continues without you. And tomorrow, the data will be there. One more point in the catalog, one more redshift measured, one more afterglow faded below detection, one more event added to the long record of the universe's most energetic moments. The story has one more place to take you, into the question of whether any of this has ever touched the Earth. You are safe tonight. That is worth saying clearly before this final part of the story begins, because what comes next involves distances and energies and geological timescales that can feel unsettling if they arrive without that anchor. You are safe tonight. The nearest candidate star capable of producing a gamma-ray burst aimed at Earth is WR-104, a Wolf-Rayet star located approximately 8,000 light-years away in the constellation Sagittarius. It is massive, it is luminous, it is losing mass at an extraordinary rate through its stellar wind, and it is rotating rapidly enough that when it eventually collapses, in the next 100,000 years or so, by current estimates, it may produce a long gamma-ray burst. Its rotation axis appears, from Earth's viewing angle, to be pointed somewhat in our direction. 8,000 light-years. At that distance, even a powerful gamma-ray burst would deliver a dose of gamma radiation to Earth's upper atmosphere that, while significant, is far below the threshold for the most severe consequences. The atmosphere is an extraordinarily effective shield at these distances. The threshold for serious biological and atmospheric damage is generally estimated to be somewhere within approximately a few thousand light-years, and even that estimate is conservative. No confirmed gamma-ray burst progenitor is known to exist within that range. You are safe tonight. But the universe has not always arranged things so conveniently. 443 million years ago, at the boundary between the Ordovician and Silurian periods of Earth's geological history, something ended approximately 85% of the marine species then living on this planet. The Ordovician-Silurian extinction is the second largest mass extinction in Earth's history, exceeded in scale only by the Permian-Triassic extinction approximately 252 million years ago. The cause of the Ordovician-Silurian extinction is not fully established. The dominant hypothesis for decades involved a major glaciation event, a rapid cooling of Earth's climate driven by the drawdown of atmospheric carbon dioxide by newly evolved land plants, which caused a drop in global sea levels and a disruption of the shallow marine ecosystems where most Ordovician life existed. But in 2004, astrophysicists Brian Thomas and Adrian Malott published a detailed analysis of an alternative or supplementary mechanism. They proposed that a gamma-ray burst occurring within approximately 6,000 light-years of Earth could have caused the pattern of extinctions observed in the fossil record. The mechanism works like this. A gamma-ray burst produces a flash of radiation lasting seconds to minutes at the source. By the time this radiation reaches Earth's upper atmosphere, if the source is close enough, the gamma-ray and X-ray photons carry enough energy to drive chemistry in the stratosphere that would not otherwise occur. Specifically, they break apart nitrogen and oxygen molecules, producing nitrogen oxide compounds that act as catalysts for the destruction of ozone. The ozone layer, the stratospheric band of O3 molecules sitting between approximately 15 and 35 kilometers altitude, absorbs biologically damaging ultraviolet radiation from the sun before it reaches the surface. Without it, the surface flux of UVB radiation increases dramatically. The thin ozone layer, measured in Dobson units, is not abundant in the absolute sense. If you compressed all the ozone in Earth's atmosphere to sea level pressure, it would form a layer only about 3 millimeters thick. That 3 millimeter equivalent is the difference between a planet hospitable to complex life and one bathed in sterilizing radiation. In the Thomas and Malott model, a gamma-ray burst at 6,000 light-years would deplete global ozone by 60 to 90% within the first year. The depletion would not be uniform. The hemisphere facing the burst at the moment of arrival would experience more severe depletion than the opposite hemisphere, creating a temporary asymmetry in UV exposure across the planet. The ozone would recover over years to decades as natural atmospheric chemistry rebuilt it, but the period of depletion is the biological crisis. Ultraviolet radiation at these levels damages DNA through the formation of pyrimidine dimers, covalent bonds between adjacent thymine bases in the DNA double helix that distort the structure and interfere with replication and transcription. Organisms with efficient DNA repair mechanisms, or with protective pigmentation, or with behaviors that keep them away from the irradiated surface, would fare better. Those without these protections would not. Ultraviolet radiation at these levels also inhibits photosynthesis directly, damaging the photosystem too complex in phytoplankton and suppressing the oxygen evolution reaction that lies at the heart of oxygenic photosynthesis. Kill enough phytoplankton and the food web collapses from the bottom. The Ordovician fossil record shows something consistent with this mechanism. Certain species of trilobites, brachiopods, and graptolites disappear suddenly at the extinction boundary. The pattern of survival shows a bias toward deeper water species, organisms that lived below the photic zone, where ultraviolet radiation cannot penetrate, surviving at higher rates than those in shallow surface waters. Graptolites were colonial marine organisms that lived predominantly in surface waters, and their extinction at the Ordovician boundary is almost total, more than 80% of species gone. In contrast, organisms living in benthic environments, on or near the seafloor, well below the UV-penetrated surface, show a less catastrophic decline. This depth-dependent pattern of survival is harder to explain through glaciation alone, which would affect shallow and deep water environments through temperature and sea level changes that do not produce such a clean depth stratified signal. It is, however, precisely the pattern you would expect from a pulse of increased ultraviolet radiation. The shadow fell from above. The deep water held. Thomas and Mellett's hypothesis is not proven. It is a plausible supplementary mechanism that is consistent with the fossil evidence, but cannot be confirmed without knowing the source, and no specific gamma-ray burst has been identified as the culprit. A burst 443 million years ago from a now dead star would leave no clearly identifiable modern remnant. What the hypothesis demonstrates is something more conceptual, but equally important. The history of life on Earth is not isolated from the broader history of the galaxy. Life evolved on this planet inside a galaxy full of dying stars. The Milky Way has produced gamma-ray bursts throughout its history. The rate was higher in the early universe when star formation was more active, but it has never been zero. Every few 100 million years, on statistical grounds, a burst occurs within dangerous proximity to Earth. The fossil record of mass extinctions, 5 major events in the last 500 million years, is a record of biological vulnerability. Each extinction has a primary cause: asteroid impact, flood basalt volcanism, glaciation, ocean anoxia, or some combination. Gamma-ray bursts may have contributed to one or more of them as secondary triggers or accelerating factors. The evidence is incomplete. The science is ongoing. But the connection is real. You are made of biology that survived every one of those events. Every extinction in the fossil record is a filter through which your ancestors passed. The organisms that died in the Ordovician are not your ancestors. They are the alternatives, the evolutionary paths that closed. The lineages that survived are the ones that happen to have characteristics or happen to occupy niches that proved durable under conditions no living thing at the time had experienced before. Resilience in the fossil record is not a virtue. It is a retrospective description of what happened to survive. You are lying in the dark, and every one of your cells carries the molecular signature of that deep history, the nucleotide excision repair pathway that identifies and removes UV-damaged DNA lesions, the photolysis enzymes that some organisms use to directly reverse pyrimidine dimers using visible light, the melanin pigments that absorb UV radiation before it reaches deeper tissue layers, the antioxidant systems that scavenge the reactive oxygen species generated by radiation-driven chemistry. These are not adaptations to gamma-ray bursts specifically. No organism evolved specifically in response to a gamma-ray burst. The timescales are too long, the events too infrequent, the selection pressure too episodic. But the general stress response machinery, the ability to detect and repair molecular damage, to mount a physiological response to sudden adverse conditions, to maintain the integrity of information-carrying molecules under environmental assault, was honed by 4 billion years of living in a world that was, intermittently and in various ways, hostile to the chemistry of life. The extinctions are part of that history, not as tragedies to be mourned. Mourning requires contemporaries, and the trilobites have none, but as selection events, filters, each one closed some evolutionary pathways and left others open. The ones that remained open eventually led here. Every cell in your body is the product of an unbroken chain of successful replication stretching back 4 billion years through every environmental catastrophe Earth has experienced, including whatever ended the Ordovician and extinguished 85% of marine species. That chain did not break. You are the proof. Let your breath slow a little more. The question of future risk is scientifically straightforward to address. WR-104 is the most discussed nearby candidate. The star Eta Carinae, approximately 7,500 light-years away, is a hyperluminous star in an unstable phase that may eventually produce a supernova or hypernova, but its rotation axis does not appear to be aligned with Earth, significantly reducing the likelihood of a damaging burst directed our way. No confirmed gamma-ray burst progenitor is known to exist within the danger threshold. The statistical rate of dangerous gamma-ray bursts, those close enough and oriented correctly to damage Earth's ozone layer, is estimated at roughly once per billion years or less in the current Milky Way. On the timescale of the history of complex life on Earth, roughly 600 million years since the Cambrian explosion, a rate of once per billion years implies a non-trivial probability of having occurred at least once. The Ordovician timing is suggestive, but it is also something else, a reminder of perspective. The universe does not operate on human timescales. The events relevant to gamma-ray burst risk are separated by hundreds of millions of years. The stars that matter are thousands of light-years away. This is not an acute threat in any human-relevant sense. It is a geological scale phenomenon, the scale at which ice ages happen, the scale at which continents drift, the scale at which the Milky Way itself rotates. One full revolution taking approximately 225 million years, during which time the solar system passes through different regions of the galactic disk, different densities of star formation, different probabilities of nearby stellar catastrophe. Your position in the galaxy tonight, in the Orion Arm, roughly halfway between the galactic center and the outer edge, in a relatively quiet region between two major spiral arms, is by the standards of galactic neighborhoods a comfortable one. Star formation rates here are moderate. The density of massive stars is lower than in the Carina Sagittarius arm, closer to the galactic center. There is a concept called the galactic habitable zone, proposed by astronomer Guillermo Gonzalez and colleagues, which identifies the region of the galaxy where the conditions for complex life, heavy element abundance, distance from dangerous galactic center phenomena, moderate star formation rate, are most favorable. The solar system sits near the inner edge of this zone. You live in one of the quieter neighborhoods of a violent galaxy. That is not a small thing. Now let the story complete its circle. You began tonight with a signal from 1967, a military satellite detecting something from the deep universe that no one could explain. You followed the science across decades to the moment a Beppo Sachs observation resolved the debate over distances. You traveled to the edge of what distance means. 13 billion light years, 13 billion years of light crossing an evolving universe. You went to the source, the collapsing stellar core, the jet forming at relativistic velocity, the neutron star merger producing kilonovae and R-process elements. You followed the instruments, Swift, Fermi, LIGO, the global network of telescopes and alert systems keeping the watch through every night. And you arrived here at the question of whether any of this has touched the Earth, and at the answer, it may have, 443 million years ago, in a way that shaped what lives on this planet today. Right now, while you breathe, slowly, deeply, your body's settling into the particular weight of deep rest. Gamma-ray bursts are occurring in galaxies distributed across the observable universe. Each one involves physics at the absolute limit of what matter can do. Each one releases energy that dwarfs anything in the ordinary scale of experience. Each one will produce light that travels for billions of years in the vast majority of directions, never touching anything, carrying its information into the dark. Some small fraction will be detected. Some small fraction of those will have afterglows bright enough to follow up. Some small fraction of those will yield precise redshifts, host galaxy identifications, environmental measurements, constraints on the physics of the jet. Each one adds to the catalog. The catalog grows. The understanding deepens. Not quickly, not dramatically. The way science always deepens, in small increments, each one building on the last, each one made possible by all the work that came before. You have been part of that deepening tonight, not as a scientist, not as a researcher, but as a mind that has held the science, moved through it, let it change the shape of what you understand to be possible in the universe you inhabit. The gamma-ray bursts will continue. The instruments will continue watching. And the universe will continue being what it has always been, vast, violent, ancient, and remarkably ordered, governed by laws that hold from the quantum scale of a nucleon to the cosmological scale of the observable universe, laws that allow energy to be released, light to travel, detectors to record, and minds to understand. There is something worth sitting with in that, as your breath slows and the boundaries between wakefulness and sleep begin to soften. The same universe that produces gamma-ray bursts, events of incomprehensible violence at distances of billions of light years, also produces the conditions for biology, for nervous systems, for the kind of electrochemical processing that, at sufficient complexity, becomes awareness, the kind that notices the dark, the kind that wonders what is out there, the kind that builds satellites and spectrographs and gravitational wave detectors to find out. The violence and the curiosity exist in the same cosmos, subject to the same physical laws, separated by scale rather than by kind. A gamma-ray burst is gravity releasing energy stored in mass. A thought is electrochemical gradients releasing energy stored in molecular bonds. Both are transformations of energy governed by the same thermodynamic principles, unfolding at radically different scales. The universe runs on the same physics everywhere. That continuity, that single consistent set of rules operating from the Planck scale to the Hubble scale, is one of the deepest findings of modern science. It was not obvious that it would be true. Early cosmologists worried that the laws of physics might differ in distant regions of the universe, or in the early universe, or under the extreme conditions near black holes. The evidence has accumulated across a century of observation that the laws are the same everywhere they have been tested. The absorption lines from a galaxy 10 billion light-years away show the same atomic physics as a laboratory on Earth. The gravitational wave signal from a neutron star merger 130 million light-years away is consistent with the same general relativity that describes the orbit of Mercury. The nucleosynthesis products in the kilonova ejecta match the nuclear physics measured in accelerator experiments. One set of rules, one universe. And you, lying in the dark, are part of it, not an observer looking in from outside, but an expression of it, made of its atoms, thinking with its physics, resting in the gravitational field of a planet that formed from the same processes that eventually, in different configurations, produce gamma-ray bursts. Let that settle, not as a concept to hold tightly, as a background, something that can be felt at the edge of awareness while the foreground releases. The room is quiet. Your body is heavy in the good way, the way that means the day has been processed and the night can begin in earnest. The universe is out there, vast and energetic and indifferent, and also in the sense that it produced you and everything you know, curiously intimate. The gamma-ray bursts are happening right now. The instruments are watching. You are resting. All three of these things are true at the same time, in the same universe, and none of them contradicts any of the others. Breathing slowly now. The room around you is quiet. The darkness is complete. The instruments in orbit are awake, but you do not need to be. Let the weight of what you know tonight rest gently in the background of your awareness. The star that died, the jet that formed, the light that traveled, the detector that caught it, the astronomer who measured it, the catalog that holds it, the understanding that grows. All of it real. All of it out there. All of it happening right now in the only universe there is. If tonight's story found you, please consider subscribing to Quiet Science at Bedtime, and if it helped you rest, a like means more than you might expect to a small channel trying to bring real science into the hours when the world goes quiet. Good night. Sleep well. Everything you heard tonight is real. Gamma-ray bursts are out there right now.